You press the power button, and deep inside the chassis, fans spin up and lights blink to life. But in that exact moment, your computer is effectively brain dead. The operating system, whether it is Windows or Mac OS, is asleep on a storage drive, and the processor is just a lifeless square of silicon. It creates an immediate chicken and egg problem. The hardware needs instructions from the operating system to function, but the operating system requires functioning hardware to load. A machine cannot wake itself up from nothing. To bridge the gap between dead metal and complex software, it relies on an intermediary layer. That bridge is the Basic Input-Output System, or BIOS. It is a highly specialized piece of firmware hard-coded directly into a chip on the motherboard. This single chip holds the absolute first set of instructions your computer executes, providing the initial digital jolt needed to wake up the memory, the processor, and the drives, and it never truly powers down. A tiny watch-like CMOS battery keeps the internal clock and these critical startup settings alive for years, even if you completely unplug the PC from the wall. This makes BIOS the true layer zero of personal computing. It defines the physical health and reality of your machine, long before your operating system even exists. Freeze the timeline mere milliseconds after you press power, and you will catch the BIOS performing its most critical job, the power-on self-test, or POST. This animated diagram shows how the system rapidly interrogates the physical integrity of its parts. It sends a digital ping to the CPU, the memory, and the cooling systems, illuminating each component as it verifies their status. If a component fails this interrogation, the system has to communicate the error before the screen can even turn on. It does this using primitive audio beep codes, like a sharp audio burst warning you of a faulty memory stick. A longer, drawn-out tone indicates a much more severe issue, usually pointing to a critical failure in the graphics card or the processor itself. The post sequence acts as an absolute failsafe. It intentionally stops a fatally wounded machine from attempting to run, which would otherwise destroy the hardware completely. This strict startup routine was conceived in the 1970s by tech pioneers, men like Gary Kildall, who needed a universal hardware standard so different software could run on the same machines. When IBM adopted this exact architecture in 1981, it established the foundational language that powered the massive expansion of personal computing. But there was a hidden scaling problem built into that original code. Traditional legacy BIOS was constructed on 16-bit mathematical architecture. This chart illustrates the trajectory of data storage requirements over the decades. By the early 2000s, that 16-bit math hit a hard ceiling, rendering the firmware completely blind to any storage drive larger than 2.2 terabytes. A routine written in 1975 successfully powered global systems for decades, only to collide with a physical data limit that the original designers never anticipated. To break that bottleneck, the industry engineered a modern successor, the Unified Extensible Firmware Interface, or UEFI. Looking back at our chart, the 2.2 terabyte barrier shatters entirely. UEFI's upgraded architecture can theoretically map storage drives up to a staggering 9.44 zettabytes. It also replaced the ancient keyboard-only text menus of legacy BIOS with full graphical interfaces, significantly faster boot times, and hardened security protocols. Back on our split-second timeline, with the hardware verified, a program called the Bootstrap Loader finally locates your operating system on the hard drive. It points the processor to the exact location of the operating system and steps aside, completing a sequence of architectural handoffs in the few seconds before your desktop appears. Because this entire process happens in the background, it creates a critical security blind spot. BIOS and UEFI run well before your operating system and its antivirus software ever load. Hackers aggressively target this exact layer. If malicious code compromises your firmware, it effectively controls the underlying reality for the entire operating system running above it. This animated model shows the mechanics of a real-world attack known as Plundervolt. External code injects into the firmware and maliciously manipulates the physical electrical voltages inside the processor to force calculation errors and steal encrypted data. Standard malware scanners operate entirely within the operating system. They look right past these low-level architectural attacks because they are searching in the wrong place. Motherboard manufacturers release firmware updates to seal these architectural gaps, providing a critical defensive layer that standard antivirus software cannot reach. The complex startup checks finish, the screen flickers, and your familiar desktop finally illuminates. That brief loading sequence hides a highly engineered bridge spanning the gap between lifeless electrical components and the digital world you interact with. So the next time you press power and hear a single sharp beep, recognize it for what it is, a 40-year-old tradition declaring that your hardware is healthy, secure, and ready to serve.